So right now, only the presentation is being seen on the screen, right?
Okay, so it started, so you can start anytime.
So should I start?
Introduce you. So it's a pleasure to have Shuchita, who's going to talk about tidiness. So of planar polygonal spaces, maybe about cleaning and tidying. Okay, Shuchita, over to you.
Thank you, Priyapat. Good afternoon, everyone. And so, as Sir has already said, I'm going to talk about tidiness of planar polygonal spaces. In what sense we'll do their cleaning, we'll see in some time. To begin with, let's see what is the main motivation for this entire talk. So, this comes from the Bourse-Coulomb theorem. So just to recall, the standard version of Bourse-Coulomb theorem says that if you have a continuous map F from Rn to Sn to Rn, then there is a pair of antipodal points which are mapped to the same point by this continuous map F. Okay. So everyone knows that antipodality is something which has much more structure than just being a name. It gives an action on Sn. So what can we say about spaces which might have an action? Can we sort of generalize this? Can we extend this Bourse-Coulomb theorem? Because as of now, we only know that Bourse-Coulomb theorem is a theorem which concerns about spheres and RNs. So moving forward, if you have a free Z2 action on a space X, then this is the question which we want to address. That if you have a map, continuous map F from this space having an action to Rn, when can we say that there is going to be a map X, such element X, such that f of X is going to be the same as f of mu of X, where mu is this action that X comes with. Okay. So this is exactly like if you put X to be Sn and the action you choose to be the antipodal action, it becomes the usual Bourse-Coulomb theorem. So the definition which we would want for a general Bourse-Coulomb theorem is this. We would say that a triple X mu Rk satisfies Bourse-Coulomb theorem, or it holds for this triple if for every continuous map F from X to Rk, there exists an X such that f of X is f of mu of X. Okay, that's exactly what we are demanding here. So the triples for which this holds are called BU triples. And we say that Bourse-Coulomb, generalized Bourse-Coulomb theorem holds for these triples. Okay. But question is, how do we really find these Bourse-Coulomb triples? It's not really easy. Here we could only see that these are Sns and you come to the antipodal action and you have Rns and the job is done. But when you have proceeded to general topological spaces with some action, how do we really go about it? So finding the Bourse-Coulomb triples is the main job, and we will slowly progress towards finding these triples in this talk. And this finding these triples also involves the data of this particular dimension k. Okay, so what it really says is that, so first of all, we can notice that if you have a continuous map F from X to Rk definitely embeds inside some R. N for n bigger, or even to say simpler things, Rk sits inside Rk plus 1. So if you have Rk X to Rk, then you have X to Rk plus 1 as well. And you will have a Bourse-Coulomb triple starting from a Bourse-Coulomb triple of this type. Yeah. So in that sense, you would want to find an invariant which does not really change with these k. And to see that, we are going to define few parameters which are related to topological spaces. But before that, we make an assumption that all the spaces which we are going to consider in this talk are finite simplicial complexes. Okay. So before proceeding to these parameters, some basic definitions, some pair X nu is a Z2 space if X is a topological space and nu is an Z2 action. So even though we always said that mu is some action, we are going to consider only the Z2 actions. This entire talk is about Z2 actions. No other actions we are going to consider. So a Z2 space is a pair with X as a simplicial complex and mu as a Z2 action on X. A very simple example which one can see is that you take n-dimensional sphere and you consider the antipodal action. Obviously, Sn is a simplicial complex, antipodal action is a Z2 action. So Sna, so this is my notation, Sna, A stands for the antipodal action. So Sn coming with the antipodal action is a Z2 space. And a Z2 space is called a free Z2 space if the action mu is free, which means no element is getting fixed. For no point of X, mu of X is X. Okay. Now, once you have Z2 spaces, the next most natural thing is to talk about map between them. So a Z2 map between two Z2 spaces X nu and Y tau, it's a continuous map F from X to Y such that it respects the corresponding actions. So if you take elements here along with the action and you go here, then it respects the action on Y, which is tau. So F nu is same as tau F. And we fix the notation that if there is a Z2 map from X to Y, we just denote it by saying that X to Y with a Z2. Okay, now we come to finally defining the parameter which I talked about, which is going to guarantee the existence of BU triples in a nice enough manner. So for a Z2 space X mu, the Z2 index of this space is defined to be the minimum n such that there is a Z2 map from X to Sna. So X is coming with the Z2 action mu, Sn I'm taking with the antipodal action, and I am asking for the least possible number n for which there is a Z2 map from X to Sn. Okay, this least number is defined as the index of this Z2 space X nu. Also, as an example, if you want to see Sns have Z2 action, Z2 index as n. This comes very easily from the Bohr-Goulam theorem. You cannot go smaller than this. There is no antipodal map from Sn to Sn minus 1, right? So the Z2 index of Sn with antipodal action, here maybe I could have said Sna is n. And one easy observation is that if you have a Z2 map from X to Y, then Z2 index of X is less than equal to Z2 index of Y. That is quite easy to see. If you have a map from Y to Sn, then composing it with this Z2 map, the composition is again a Z2 map, and we'll see that the index of X cannot exceed the index of Y. Okay, so now on, just to simplify notations and saving my energy, we are just going to talk about index. So I'll write index in place of Z2 index, even though we'll be meaning Z2 index all the time. Okay. So notice that all this business which we did here is about taking X and going into Sn, right? What if we do things the other way around? That is, if we look at Z2 maps from Sn into the space X, that is another invariant, and this is called co-index. So co-index of a Z2 space X mu is defined as the maximum n such that there is a Z2 map from Sn to X, where Sn is considered to be the antipodal action. Okay. So see the contrast, we wanted the index to be the minimum possible Sn into which X can be mapped into, whereas co-index is the highest Sn from which there exists a map into X. So this notion is in some sense a dual notion to the in which we have defined. And again, as a very simple example, if you consider the n-dimensional sphere with antipodal action, its set to co-index is n for any n, right? Again, the same logic applies. Also, one can see that co-index for any, okay, there's a typo, this Z2 should have been here. So co-index cannot be lesser than 0. And co-index is always less than equal to the index, right? Because you could have otherwise composed the maps Sn to X to, if there is Sn minus 1, then you would have gotten a map from Sn to Sn minus 1, which is a Z2 map with antipodal action, and that is been forbidden by the Bourse-Coulomb theorem. So co-index is always less than equal to the index of X, which in turn is always less than equal to the dimension of X. Dimension of X is the highest which you can go, right? So again, for the rest of the talk, we are going to write co-int for the Z2 co-index of a space. Now, we have seen this in the topological sense, just a little diversion, and we see what these definitions would take the form of if we are into graph theory. So if we replace the topological space X by a simple graph G, where simple just means that it doesn't have any loops and there are no multiple edges existing, and the n sphere Sn being replaced by the complete graph on n vertices, which means any two distinct vertices are connected by an edge, then notice that a graph map F from G to Kn actually gives a proper coloring of G, which means if you have any edge in G, then the endpoints of any edge are given different colors, right? That is the definition of a graph map. So any map F from G to Kn gives a proper coloring, and then to contrast it with the definition of the index, you would want to look at the smallest possible n for which such a map exists. And that is nothing but the definition for the chromatic number. So int of G in the setup of graph theory gives you the chromatic number of the graph. Similarly, if we analyze the co-index, then notice that any graph map F from Kn into G gives a clique of G. Yeah. So if you're asking for the biggest enough n such that there is such a map, you are asking for the clique number of the graph. Therefore, the co-index of G is the clique number of the graph omega G. Okay, coming back to our original business, we saw the co-index and index, and we also saw the inequality that co-index is less than equal to index. But is it like there should be cases when it is strictly less, there might be cases when it is exactly equal, and what are these cases? We'll see now. So a Z2 space X is called tidy if its index and co-index are same. Okay, so when they happen to coincide with each other, we call the space tidy. So the in-between garbage has been thrown out and the space is clean to be called tidy. Very quick example is, we have already seen that the co-index of the Sn with antipodal action was n, so was its index. Therefore, the Sn along with A is a tidy space. Okay, and so this Sna is tidy for every n. But then the next obvious question, are there any other examples of tidy spaces? Are there examples of non-tidy spaces? Well, tidy spaces is something which is closely related to uh, Bourse-Coulomb triples also. So that is the next part of the talk, but let's just first see that there are few examples of non-tidy spaces. So one can consider the torus S1 cross S1 and see that it is non-tidy. To see it, it's very, so of course, the index is bounded from above by the dimension of x. Therefore, the index of a torus is less than equal to 2 and the co-index is greater than equal to 0. So we will see that the co-index is actually 1 and the index is 2. Okay. So suppose the co-index is 2 instead of 1. In which case one would get that the space is tidy, but we are saying that it is not tidy. So on contrary, suppose that the co-index is indeed 2, then you have a map from R2. Since R2 is its universal cover, you have a map from R2 to the torus, and any map from S2 to T2 will factor through this map. But then this factorization on the one side, since R2 is contractible, is going to give you the trivial, sorry. So S2 to R2, if you have a map, then Bourse-Coulomb theorem tells you that there is a pair of antipodal points which is going to go to the same point. So F tilde of minus x is same as F tilde of s, but then this cannot factor through the map which we started with. Okay, so that is easy to see that the universal cover gives you information that there is no map from S2 to T2, which is Z2 map. Therefore, the co-index is less than 2. Okay, and to see that index is bigger than 1, we can consider the homology groups and find that the trivial morphisms on one side and on the other side you have a non-trivial morphism. But to cut short that, there is a paper by Matsushita where given any n, he constructs topological spaces with Z2 action such that the index is n, however, the co-index is 2. Okay, so there are plenty of examples for the non-tidy spaces also, however, they're difficult to find and compute, but we do have spaces that are non-tidy. Coming back to tidy, we will have to deal with such an equation, which is this, but it's always extremely hard for spaces like even for torus, there is a lot of calculation involved. So when you have any more involved spaces, these computations are extremely hard. So then we look for more invariants which might give bounds on these, okay? And one such parameter is the Stiefel-Whitney height. So let's just quickly go through what the Stiefel-Whitney height is. For a Z2 space X, there is a map from X to the S infinity with antipodal action. And this then induces a map from X mod Z2 to S infinity mod Z2. But S infinity mod Z2 is RP infinity. This is going to give you a map on the cohomology level from H1 of RP infinity to H1 of X mod Z2. Now, this is the this ring is nothing but Z2. So let's Z2 be the generator of this ring. Then the first Stiefel-Whitney class is defined as the image of this element under F1 bar. Okay, so omega 1x bar is, which is the notation for the Stiefel-Whitney class, is defined as the image of this generator element under this map F1 bar. All right, and once we have this, Stiefel-Whitney height is the highest power of this element, which is non-vanishing. So Stiefel-Whitney height of x is the largest integer k such that omega 1 of x raised to k is non-zero. Okay, and this is denoted as ht of x. Now, the more important thing which we talked about is that this is a parameter which fits in between of co-index and index. So far we already knew that co-index is something which is greater than equal to 0, less than equal to index. And now we have a height which is greater than equal to co-index but less than equal to index. So when we are looking for tidy spaces or non-tidy spaces, if instead of the index or co-index, we are able to get relations between co-index and height or height and index, then also we are done. Okay. Now coming to the equivalent versions of the Bourse-Coulomb theorem. What we say is that a triple x mu rk is a BU triple if and only if height of the space x is k, if and only if its index is at least k. Height is k automatically implies that index is at least k because of this, but the other way to inequality to equivalences are not so easy to see. And I should remark that there are many more equivalent versions of saying what a BU triple is, just how we have several versions of the Bourse-Coulomb theorem. There are several equivalent characterizations here for the BU triple. But for this talk, since we would be needing exactly just this much, I have only listed out these two equivalent conditions. Okay, and now once we know what a height is, let me remark back to the point where, okay, that is not there. The example of Matsushita, which I told he has constructed, is that he constructed the spaces xn whose height is n instead of the index. So height is full, whereas the co-index is just 2. And that's how we get non-tidy spaces. Okay. Now, having all these in picture, coming back to our original motivation of finding the BU triples, well, so what are the candidates? Where do we search for these BU triples? And one such place where we are going to explore these is the space planar polygonal spaces. Also, why we care about the BU triples is that in topological combinatorics, BU triples or rather tidy spaces are in some sense considered as the spheres with antipodal actions. So because we have already seen for spheres, these are tidy. So in the topological combinatorics, people are really interested in finding spaces that are tidy and also the spaces that are non-tidy. So the place where we are going to look for these are the polygons, which are orientation preserving, which we are going to consider the ones which are. So we are going to consider the planar polygonal spaces up to orientation preserving isometries. Before that, let's just define what it is. If you have n rods, okay, and then n length vector you consider. So L1, L2, Ln. L1 is the length of the first vector, first rod, L2 is the length of the second rod, and so on. Then, and arranging these lengths in the increasing order, we define the moduli space of polygons up to orientation preserving isometries as the vector u1, u2, un in the product of S1s, because each vector can rotate into S1 when I'm seeing them on the planar plane, such that they are closed. So Li ui is 0 modulo the SO2. Okay, so they are preserving the orientation also. Okay, so a remark is that ML actually supports a Z2 complex structure. And this complex structure is given by Panina, and it also has a Z2 action, where Z2 action is the reflection along the x-axis. Okay, another modelized space of polygons which we take is the one which you have up to isometries. So here you take these same vectors, but you now mod it out by O2. Okay, so you have identified the copies which were reflection of each other across the x-axis to the same element, and that is my ML bar. So clearly ML to ML bar is a twofold cover. And as I've already said, the Z2 action is reflection across the x-axis. Okay. Now with these MLs, the main thing which is into picture is this length vector. Depending on what length it is and how these LIs are related to each other, the modelized spaces would change. So there is a short subset system which we define here, and there are few notations. So a subset of N is a short subset with respect to the length vector L if the lengths adding the lengths of the Li corresponding to the coordinates of S is strictly less than the remaining lengths. Okay, and it is long if it's the other way around. So if this is bigger than this, then you call that subset as a long subset. And in this talk, we are going to consider only the generic length vectors, which means that if you take any subset, it's either short or long. You're not going to consider the subsets when there is an equality here. Okay, we want strict inequality. And an interesting fact to see is that the family of short subsets form an abstract simplicial complex. Because if this length is less than this, if you take a subset of this, that length is going to be this length plus some more thing added, right? So it really forms an abstract simplicial complex. Now, if L is generic, let's see a few examples. So ML is a closed orientable manifold of dimension n minus 3. N is the length of this vector L. Also, ML is going to be homeomorphic to Sn minus 3 if and only if the only short subset that contains n is the set n itself. Okay. So with these two basic examples, we proceed further. And we see a partial order on this set. Yeah. So if you take the power set of the two, then any two subsets are comparable in the sense that Si, S1, S2, SL and T equals T1, T2, TR, then Si, if that's less than equal to Ti for every I, we say that the set S is less than equal to the set T. Okay. And with this in mind, you consider the maximal elements in the set of short subsets that contain n. So we are not interested in all possible short subsets. We are considering only the short subsets which contain n. And then we look at maximum elements in this collection, and these elements are called genes. And the genetic code of a length vector L is the collection of all of its genes. Well, if S is a gene, you remove this N from here, and what you're left with is a G. So S minus N is a G. Also, if you have taken any subset of N minus 1, then this is a sub G if S is less than equal to T for some G. Okay. So few examples. If length vector L is 1, 1, 1, 1, 3, So here see that the n is 5, 1, 2, 3, 4, 5. Then the only gene which it has is 5, because the total length is 1, 2, 3, 4, 5, and the last element itself is 3. So if you add any more thing, it's going to become 4, and that's going to leave only just one more item. So only gene is the singleton 5. So therefore, the genetic code is singleton 5. Therefore, there is no G. Okay. And this, there is no sub G as well. Another little lesser non-trivial example, if you take the length vector L with all rods of length 1, then the only gene is the singleton 5. Sorry, not the singleton. Only gene is the set 5, 4. Then the genetic code is only this gene, which is the 5, 4. What are the G's? Only one G is there, which is 4. You remove the N from it, and this is the G. And then the collection of sub G's is the empty sub G, and then all the elements which are less than equal to this. So 1, 2, 3, 4. Okay. Having done all this exercise, we now come to the real job, that we want to understand the BU triples, and for that we first need to understand the cohomology ring of the moduli spaces. So Hausmann and Knudsen have shown that the cohomology ring with Z2 coefficients of m bar L is generated by classes R, V1, V2, Vn, in which are one classes, subject to the following relations. First relation says that RVI plus VI square is 0. Vs, which is defined as the product of VI's, is 0 unless S is a sub G. And for every sub G S with cardinality at least n minus d minus 2, there is a relation that summation of r raised to d minus small t Vt is 0, where t is running over all those sub G's that do not intersect S. Okay. Oops. Okay. So what is written here as a fact is that the R, the one class R, is actually the Stiefel-Whitney class of ML. Okay. And another interesting fact which you can see here is that since H star of ML bar is generated by only these classes, and this particular condition takes care of the fact that the first condition takes care of the fact that as soon as you hit any, let's say, Vi raised to k, then this can be replaced by R into R raised to k minus 1 into Vi. So if you mod out H star of ML bar by the class R, it's a Stanley-Reisner ring, and this corresponds to monomers where the non-faces would vanish. Okay. Now we see some computation for the co-index and index. So to start with, I have taken the spaces with the genetic code n comma b. Okay, so the length vector is such that the genetic code is n comma b. So then G's is the singleton b, and sub G's are the empty G 1, 2 up to so on b. Then the relation R2 implies that any two distinct VI's are going to be 0, because only sub G's that are possible is these VI's. And if you take the sub G, let's say S equal to 1, then for any D greater than equal to n minus 3, because n minus modulus cardinality of S minus 2, so that is 3, let this number be m. The sub G's that are disjoint from this S are the empty sub G 2, 3 up to B. So when you put them in this relation, for S equal to 1, you're going to see that all the sub G's that appear here give this, and I get this relation RD. RD corresponds to the T equal to empty, and the rest of the T's gives these Di's for I from 2 to B, and this is 0. Okay, so this we have done for a particular subg S equal to 1, but we know that R3 gives a relation for every subg which has this condition. So if you take S equal to J to be the subg, then the relation R3 gives that RD summation, this entire thing is 0. And now if you compare for any two different J and J primes, this particular relation gives you that RV1 is same as RV2, which is same as RV3, and so on up till RVB. Okay, and these things now I can put back in this to get that RD is actually equal to the summation RD minus 1 V1, where I ranges from 2 to B. So this is nothing but B minus 1 many samans of this object. Now, if D is equal to M, then I have Rm to be B minus 1 of Rm minus 1 V1, just substituting M here. So just keep this in mind for a while, and we take a little different direction that if we, or rather a trick, if you have the length vector L to be this, whose genetic code is only this, then taking this out from here and adding to this length, I get a reduced length vector L prime, which has as elements L1, L2 up to LB minus 1. This one is skipped, LB plus 1, and so on till Ln plus LB. So here it was Ln minus 1, and then directly I jump to Ln plus LB. So the genetic code for this length vector is the singleton gene, and gene also is a singleton element n minus 1. And recall that whenever the only subset containing n is the only short subset containing n is n itself, then the ML is homeomorphic to the sphere of dimension n minus 3. Therefore, with this, we know that M of this particular L prime is homeomorphic to S M minus 1. Okay, M was n minus 3, so one lesser dimension is n minus 1, and also ML prime sits inside ML. Therefore, the coindex of ML is at least m minus 1. So coindex of this is at least as much as the coindex of this, but the coindex of this is m minus 1. Therefore, coindex of ML is at least m minus 1. Therefore, so far we have this inequality. Coindex is bounded from below by m minus 1, and then it is less than equal to height, less than equal to index, less than equal to dimension, which is m. And in the equation which we have here, Rm is equal to B minus 1 Rm minus 1 B1. Notice that Rm minus 1 cannot be 0 because height is at least m minus 1 due to this. Okay. Similarly, V1 cannot be 0. Therefore, why V1 cannot be 0? If V1 is 0, then all these relations are 0. Okay. So I know that in that expression, neither Rm minus 1 is 0 nor is V1. Therefore, for this Rm to be 0, only B minus 1 could be 0, which means B minus 1 could be congruent to 0, since we are dealing with Z2 coefficients. This is same as saying that B is odd, and in which case Rm is going to be 0. Then by the BU triple equivalent versions theorem, we will see that this particular triple is not a Bourse-Coulomb triple because Rm is not non-zero. It would have been a Borsuk-Ulam triple if Rm was non-zero, but Rm is zero, therefore it is not a Borsuk-Ulam theorem. And hence, index cannot be bigger than m. Therefore, index is less than or equal to m minus 1. Putting all these together, we get this inequality sandwiched between the number m minus 1 on both the sides. Therefore, what we have got is that for B odd, this entire calculation tells us that the ML with its genetic code is tidy. Okay. What happens if B is even? That is being dealt now. So notice that. So here I'm going to give only the steps of the proof because full proof is going to be very tedious. So ML is homeomorphic to a connected sum of S1 cross Sm minus 1. Okay. So for m equal to 2, this actually means that it's a connected sum of tori, S1 cross S1. And this we already know is not tidy. You use the pretty much the same argument which we did for the torus, and we get that the connected sum of torus is also not tidy. So now let's just focus for m greater than or equal to 3. The universal cover of m tilde L for this space is actually, we show that it is homotopic to a wedge sum of spheres, infinitely many wedge sum of spheres. And there is a result which says that the co-index and index, if that is K, then the kth homotopic group of X has a Z summand. Okay. So suppose for B even, the co-index of ML is also M. So, okay, maybe I didn't say that earlier, but yeah. So this was the case when Rm was 0 and Rm turned out to be 0 only for B odd. So B even actually tells you that Rm is non-zero. And hence, by this theorem, this is a BU triple. And therefore, the height is full and hence the index is also full. Okay. So at this place, to show that something is equal to index, I know index is m, so I'm assuming the co-index to be m. Then, since ML, m tilde L is a universal cover of ML, the mth homotopic groups of ML and m tilde are isomorphic and they should have a Z summand. Okay, by this result. And let's just see the computation for the mth homotopic group of the covering space. So this is defined as the colimit taken over finite subset of Z pi m of wedge space wedges over Sm minus 1, which is this sum, but pi m of Sm minus 1 is Z2. So this colim has only two torsions and there is no free element. Therefore, there is no Z summand in this. And then using this result, we know that there is no Z summand in pi m of ML, which is a contradiction. Therefore, the co-index of ML is m minus 1. Okay, so this is an equality which we get. So m minus 1 is the co-index, which is strictly less than height because height and index both are full. Therefore, ML with genetic code NB is non-tidy for even values of B. All right. So this was the calculation when the ML, when the genetic code was NB. We'll do some more hard work and see another calculation when the genetic code has more than one genes. Okay, and here is the calculation. So, and this, after all this, what we really get is that for even values of B, the space ML is tidy. So we have considered the genetic code with two genes. One of the genes is NB, another is N42. And for this, the calculation is shown here, which I am sure you should not be able to read. But for this, if B is even, ML is tidy. And there are some more calculations which we have done, and some of these exist in literature also. These are the calculations. So if let's say the genetic code is N, we already know that the co-index, height index, everything is same. And thus it's a tidy space. Does it give a BU triple? Yes. What are the possible BU triples? The corresponding ML with the action and the R raised to N minus 3 is a BU triple. Okay. For NB, we just did the calculation and saw that for B odd, it's a tidy space. For B even, it's a non-tidy space. And since we know the index in both the cases, they do give us BU triples. And these are a few more calculations. If the genetic code happened to be of this form, then the co-index turns out to be this, but there is no information we have for the index, and therefore we do not know if the space is tidy or not. And since we do not know the index value, we do not know if it's going to give a BU triple or not in this dimension. Okay, so these are some more spaces informations. And if I take the polygonal space with length vector 1 1 1 1 1 comma r, then depending on the value of r, there are few more calculations. So if r happens to be the number n minus 2, then there are no conditions and we know that the space is tidy. Thus it gives a BU triple. For n equal to 4, we have to split it up in the even and odd case, and we get that for even spaces, for even and the space is tidy. For odd n, the index is n minus 3, but the co-index is either n minus 4 or n minus 3. So we don't know if it is tidy, but certainly it gives a BU triple, and so on and so forth. So we have a lot of examples for the BU triples here. So how much time I have?
Sorry, I was on mute. I didn't realize. Yeah, maybe like 5 minutes.
Okay. So we have seen that in all these tables, like computing co-index, index, everything is pretty hard. And height, which comes in between, sometimes is a real rescue for both of these bounds. So let's just see some more importance about it. So the Stiefel-Whitney class R, why do we really care about this? Well, we do care about it because this computation is hard and the expressions are generally complicated. For instance, if we consider the paper of Kamiyama, he has shown that for the length vector 1111r, the height of ML is less than equal to a number. Okay, it's not even the exact height. The height is, there is a bound given on height in terms of a number. This number is this huge object, where this again is defined in terms of a complicated expression. So therefore, computing the co-index and index gives bounds on height. And the good part is that these computations of the ML spaces are actually being done all in terms of the genetic code. So the expressions at least are less complicated to look at. They may not be easy, but at least the complications of the expressions are lesser. And also the height of the Stiefel-Whitney class gives a lower bound on the cup length, which in turn is a lower bound for the LS category. Therefore, to compute LS category, height of the space gives a lower bound. So that's another application why, and another reason why we should care about the Stephen-Witten class R here. And what do we take further from here? So remember we did a small trick that if we could look at a genetic code and take a gene, pick up all the elements from the gene, add them up to the last element of the length vector, and then we can move further in the sense that if N A1, A2, AR was a gene, you take the lengths of the rods corresponding to these numbers and add them up, then the reduced length vector is a N minus R length vector, and its genetic code is the singleton N minus R. And thus the co-index is at least N minus R minus 3. What we would like to conjecture, depending on the various cases which we have seen, various calculations that we have done, is this, that if the size of the smallest g is k, then the co-index is indeed n minus k minus 3 and not any bigger. So this actually is a equality. So if you have the co-index to be n minus k minus 3, most of the problems in this table, when you are hitting or less than equal to here, would be solved. Okay, so in such cases, you would see that there is a clear gap and the spaces becomes non-tidy. And even here, all these gaps that you see. Yeah, so this is the conjecture we have. And these are the references which I have used. This is a paper where the cohomology structure of the polygon spaces is given. And here various versions of the Bourse-Goulam triple are given. This is the paper from where the Kamyama's result on the height of Stiefel-Whitney class R has been taken. Yeah, that's it. Thank you.
Thanks, Shuchita. So it's open for questions. So if there are questions, please go ahead and ask.
Oops. Yeah, any questions?
Oh, yeah, I don't see any questions. There are,
Okay, either nobody followed or everybody followed everything.
yeah, I think there are co-authors in the audience. So if they ask questions, yeah, well, that's not good for them. They should already know this stuff. So they're not. Yeah, it seems. Don't. Okay. Thanks, Shuchita.
Thank you,
Thanks.
sir.
Thanks.
Thanks.